All right, now here is an example of a pipe flow system where we have to consider parallel pipes. So a system that has a parallel pipe flow. So this is a system here, where the red dashed line pipe is not a current component. Let's say so, just a single pipe connects tank A and B, and then you'll get some flow between A and B for this system. And the goal in adding a second pipe that connects here down to the bottom of tank B is that it'll increase the flow rate by 30%. So the Q value we have for the single pipe is then increased, 1.3 total volumetric flow rate for the full system when we've added the second pipe. Um, so the right, so for our parallel flow ideas, the general solution method, the general concept here is that the flow rate in one will then increase by 30%. You'll get 1.3 times what it was for just a single pipe, but then it gets split between 2 and 3, so that the total flow between 2 and 3, the sum of the flow in 2 and the sum of the flow in 3, must equal the new flow, that 1.3 times the old volumetric flow. Let's see, we don't need to find the friction factor here. It's given as 0.02, and we don't need to consider minor losses. They are negligible in this case. The goal here is to then say what diameter does this pipe need to be in 3, the added pipe diameter need to be to make the flow rate increase by 30%. This section is 600 feet long, this section is 500 feet long, and we're just saying this change in elevation is pretty negligible, such that this is also, the new section is also 500 feet long. Technically we need to consider how far it drops, but it's going to be small. The heights here are small compared to the lengths. And that's, again, to get us a fully developed flow for most of the pipe system. Okay, so to get at this, again, we'll be applying the energy equation a bit here, and then we have to use the parallel ideas. But we're going to be applying energy, and it's a good choice here is to choose the free surfaces A and B. So I've labeled the free surfaces as A and B, even though the tanks are also called A and B, but when we apply the energy equation, we're talking about between the two free surfaces. And then the pipe sections we'll label here as 1, 2, and 3. And pipe 3 is the new section. Okay, so we need to start by relating and calculating what the old volumetric flow rate is. It's not given in the problem statement. We can do that by just considering the single pipe, so just pipes 1 and 2, and applying the energy equation from A to B. Here we have the total head at A, the total head at B, plus our major losses for that first pipe and the major losses for the second pipe. Go to now some simplifications. Our pressure at A equals the pressure at B. They're both atmospheric. Our velocity at A and B are both 0 because these are big tanks. It's negligibly small velocity at the free surface. The change in the height is given in the problem, in the diagram there, as 25 feet. That A is higher than B. The diameter is given in the problem statement as 6 inches, or half a foot for both pipes, pipe 1 and pipe 2. The length of the first section is 600 feet. The length of the second section is 500 feet. The friction factors are assumed to be equal and 0.02 given in the problem statement. And then we know that the velocities for the two pipes are equal. We don't know what they are, right? So in our energy equation, we have velocities at the free surfaces, which are 0. But then our major losses are the velocities in the pipes, which we don't know yet. That's going to be part of the calculation. In fact, it's the only thing unknown in this entire equation. So if we simplify this, we're going to cancel, 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 cancel. All that's left on the left-hand side is just the height, the difference of ZA minus ZP, which is 25 feet. And then we can combine our major losses here because everything is the same except the length of the two pipes. So they both have the same F value. They both have the same D diameters. They both have the same velocities. 2G is obviously the same, but the 600 feet and 500 feet are just then added together. Solve this for velocity to be about 6 feet per second, and then we can multiply that by the area, which is pi over 4d squared, to get the volumetric flow rate for the single pipe system. Okay, we then now know that when we add in the second pipe, the constraint there is that it increases the volumetric flow rate by 30%. So we have a 1.3 factor times the single pipe volumetric flow rate. gives us 1.4544 feet cubed per second. And so that is going to be the volumetric flow rate in the first pipe, which is then now split. So the volumetric flow rate here is that 30% increase, but then now that's going to equal the sum of the flow rates through pipes 2 and pipe 3. So our sum of Q2 and Q3 is given by that volumetric flow rate. To then separate these two and actually determine what they are, to then get at what that diameter of that third pipe needs to be, we then apply the energy equation from A to B through the two different ways it can get there. So first, through that the old, what used to be the single pipe system. So we'll go through pipes 1 and 2. We apply the energy equation. Again, it doesn't look any different. All the same cancellations we did before is the same, except now the velocities are going to be different in the two pipes. We know that the velocity in 1 is just the volumetric, that total volumetric flow rate, which we actually know here, divided by its area. So its velocity is now 7.864 feet per second. And the velocity at 2 we don't know. That's going to be the volumetric flow rate at 2 over its area, but we can't separate this from Q3 at this point. So if we plug everything in, put in the right lengths, keep them separate in this case, we now know that the only unknown here is the velocity at 2, right? So we use the energy equation through pipes 1 and 2, where we already know the diameter of pipe 2. We do that to find the velocity through the second pipe, and then we can then go back up into here to then determine what Q3 is, to then determine what the velocity in that third pipe is. And that's what we do down here, applying the energy equation from A to B, but instead now we're going through the new pipe section, pipe 3. We still just get the 25 feet. The energy equation is applied here, it's just the losses are going to be different. So both of these combined, I'm just taking, this is the same as up here. So we've already done the work here, these two terms, we're combining them here. And then all that's different over here is now we just have this quantity is just equal to the major losses through pipe 3, where V3 is the unknown quantity. V3, and I should also say we don't know D3. We don't know the diameter of that third pipe either. However, now that we know Q2, we can determine Q3 by solving this equation here for Q3. We know that, so here's our Q3, and then we can then divide that by the area to determine, or to get an expression here for the velocity through the third pipe. But now this expression is going to be a factor of the diameter of the third pipe. All right, so we see the diameter showing up in just the major loss term, and we also see the diameter squared showing up in the velocity, which is also itself squared. So within the velocity, we have a 1 over diameter squared, and that's squared itself. So this is a 1 over diameter to the fourth, and then another diameter on the bottom. So really, we have an expression here for the diameter to the fifth, and we can solve for that by getting the diameter to the fifth. Basically, just take all your diameters, bring it over here, and then divide by this 1.9545, and pull that over to the bottom, the denominator over here. And then take a fifth root, a 1/5 power here, to determine that the diameter of the third pipe needs to be about 2/3 of a foot, or a little bit over 8 inches. So it's a slightly larger pipe than the other pipes in the system, which were 6 inches. This new pipe needs to be 8 inches.